Hello, how's everybody doing today? My name is Gavin Crawford. I'm a civil engineering student at California State University of Long Beach. And today I'll be discussing the lab operating characteristics of Pelton turbine. Due to the unfortunate circumstances going on in our society, I will be recording this and presenting it at home. Okay, so here's a list of all the topics I'll be discussing today. First, I will give a little introduction that describes the background and overall objective of this experiment. Next, I will discuss the experimental method we used for this lab. This goes over things such as procedure. Last, I will talk about the data we conducted, the graphs we displayed, and a conclusion, talking about what these numbers mean. When conducting a lab, my biggest question is, why is this lab important and where did it come from? Doing this presentation was great because it provided insight on where this idea came from. It originated from an engineer named Lester A. Pelton, a man from Ohio. Although there were many different people trying to perfect the Pelton water wheel at one time, Lester was the only man to do so. It all began when Pelton was working in the gold mines and noticed that a reliable source of power was needed to drive the equipment. Although steam engines were a primary source of power and it provided sufficient results, it wasn't sustainable. Pelton then created this water wheel. The water wheel was simple, but extremely useful because it used water momentum to transfer power. The Pelton water wheel had laid a foundation for next generations to create highly advanced hydro turbines used at hydroelectric and water power plants today. Now that we understand the Pelton turbine a little more, we will now analyze this lab. The main objective of the experiment is to see how various conditions can alter power and efficiency with the Pelton turbine. This will be done throughout many different speeds. Here is some of the equipment that was used in our experiment. In the top right corner, we see the hydraulic bench, which is measured using water discharge that can help us determine things such as flow rate. Below is a smaller version of the Pelton turbine itself. And lastly, to the left, we see the spring balance. Increased tension in this helps with our brakes. Listed here is a procedure we followed while conducting the experiment. Performing this experiment, we were analyzing the differences and similarities between a full spear valve and a partially open spear valve. For those unaware what a spear valve is, it basically is a little nozzle that shoots water at a Pelton wheel to make it turn or spin. Making it short, I will briefly cover how we went about this lab. We first used a hydraulic bench flow rate of water to spin the turbine. This flow rate had entered the spear valve completely open and was measured in cubic meters per second, given 5 liters of water. We then recorded the speed of the turbine with a device called a tachometer, which measured the speed in RPM, or revolutions per minute. Once we've reached our maximum speed, we added tension to the mechanism to essentially slow it down. We also had to record other important data, such as pressure gauge and spring balance readings. We continued to add this tension for 6 different sets of data. Once completed, we turned off the hydraulic bench and completed the data once again. This time, we did with the spear valve partially open instead. Here is our data for the spear valve completely opened. The column on the left displays our rotor speed, or how fast the rotor was turning. The difference in these two readings are spring balance readings. This tells us how much brake power was used in newtons to slow down or stop the turbine. Next, we have our volume. This is our volume of water in cubic meters over our time. To collect 5 liters of water gives us our flow rate shown here. In the last 2 columns, we have our hydraulic power in watts and our overall turbine efficiency. Hydraulic power is basically the use of pressurized water to create power. We measure our overall turbine efficiency using our brake power divided by hydraulic power times 100. Something interesting in this set of data is that our torque is at a maximum when the rotation speed is at 0. This is because the turbine is attempting to overcourse its force applied on the brakes itself. Now below, you will see our graph. This graph is a bell curve graph. This graph displays the brake power, torque, and turbine efficiency versus rotor speed on the x-axis. Next, here's our data for the spear valve partially open. As you can tell, the graph and the data look relatively similar, because it is. However, the spear valve partially open has a higher rotor speed as shown in the first column. Also, we see that the overall turbine efficiency had also increased, which means that the braking power is too strong for the overall power, causing a significant increase in the turbine efficiency. Below, we see a graph similar to the one shown previously. Both graphs have a similar shape and share some of the same values, but this one graph does reach a higher peak than the one just showed. One may ask after seeing the data how we came across these values or how they were derived. Here is a list of some of the useful equations that helped us get these values. Our rotor speed was a value in the tachometer in RPM divided by 60, a value that is used to convert minutes to seconds to give us hertz. The average volumetric flow rate was discussed previously, but for those who missed it, it is calculated by measuring the time it takes up to fill a 5-liter tank of water. This is in volumes, cubic meters over time. Torque is measured by using the brake force calculated above times R, which was given to us, and is 0.03 meters. Brake power is calculated by using the equation shown. It yields T, which is torque, and N is in RPM. This value units is in watts. Looking at the hydraulic power equation, one may think it looks intimidating, but it's really not. All the values are pretty much given. It's just a matter of calculating them. The only value we haven't calculated in that equation is the pressure head, HI. This value is solved using the formula to the right, where PI is the pressure difference over the specific weight of water. The last equation was overall efficiency. Again, I discussed this formula 2 slides ago, but for those who missed it, it is the brake power of the system over the hydraulic power. To conclude, both sets of data showed a trend of what we would expect when comparing the open valve versus the partially open valve for the Pelton turbine. These tests both retained a parabolic curve given by an increased tension, also known as brake power, just after the maximum point of efficiency. Looking at these graphs, it is shown that the maximum efficiency has slightly increased when the valve was partially open. The open valve showed a maximum efficiency at around 57%, compared to that of the partially open valve, which was approximately 67%. In other words, this overall efficiency was dependent on the most balanced speed with a high head of water. Anything less or insufficient would not provide the momentum needed to drive this force. In addition, the maximum power for the open valve was 18.3 Hz, while the partial valve yielded a power of 23.3 Hz. Not only did it have a much higher maximum power, but it had a much larger rotor speed at 43 Hz compared to the open valve at 35.8 Hz. As a result, the partial valve was able to reach its peak more efficiently. Overall, we see an increase of torque, horsepower, and efficiency when switching to the partially open spear valve, which shows it is a more effective approach. Alright, so this is a slide where I am supposed to ask questions. Unfortunately, because I am unable to answer questions in person, we will have to use a different alternative instead. I'll be more than happy to answer questions in the comment section below. And for the last slide. The last slide is some of the references I use for extra information regarding the lab itself, background, and much more. Well, thank you everybody for watching, and I hope you have a great day.